All right, so at this point in your biochemistry class, you've probably been introduced to all of the 20 proteinogenic amino acids. Sometimes you've maybe been introduced to 21 proteinogenic amino acids. Now, what I want to focus on here is I want to focus on your two negatively charged amino acids. Those two amino acids are aspartic acid and glutamic acid. So ASP and GLU. These are the three-letter codes for those two amino acids. Aspartic acid has a single letter code of the single letter D, and glutamic acid has a single letter code of the single letter E. Now, I like these two amino acids because it's kind of easy to remember that, well, these are your two amino acids, the only two amino acids that will have R groups or that will have side chains that have negative charges to them. Now, the way that I like to draw amino acids is I like to draw them fully protonated. So I'm going to draw both aspartic acid and glutamic acid in their fully protonated state. Now, the first thing that I'm going to do is I'm going to draw the backbone, NCC. I'm going to do that for both of them. I'm going to go ahead and try to draw both of them at the same time. Now, when these two amino acids are completely protonated, both of their backbones will look like this. You have NH3 for your N termini. Now, with an NH3, that's a nitrogen with a total of 4 bonds to it. 1 nitrogen-carbon bond and 3 nitrogen-hydrogen bonds. When you have a nitrogen with a total of 4 bonds to it, that is an atom that is going to have a positive charge. Okay, now moving on to my carbon. This is an alpha carbon, and this is where you'll find your R group, and on the back of it, you'll also find a hydrogen placed. Okay, now the last part of our backbone is going to be that carboxylic acid. So that's going to have a double bonded oxygen and an OH. Now this is drawn as a carboxylic acid and not as a carboxylate ion. This is when it is completely protonated. So I always like to visualize my amino acids have been drawn when the pH is as low as it can possibly be. Now, to complete my side chains, the R groups for these two amino acids, well, they're both fairly similar to one another. I always like to think of aspartic acid and glutamic acid as like siblings, and one's taller than the other. Okay, so aspartic acid has CH2 and then a COOH. Glutamic acid is the taller sibling. It has 2 CH2s and then the carboxylic acid. Okay, so there's my structure for both the aspartic acid and glutamic acid. Now, like I said, this is when these two amino acids are completely protonated. Well, how do you know when they're completely protonated? What you have to do in order to understand that is you have to understand how these 3 different groups, our 2 carboxylic acids and our amino termini, how those change based on solution pH. Okay, so I've circled my 3 groups on both aspartic acid and glutamic acid that are ionizable. Now, for the N termini of aspartic acid, I have a pKa of 9.90. Now that's a number that, depending on the resource you use, it might vary a little bit, but it's probably going to be, plus or minus 0.1. So maybe you'll find it as low as 9.8 or as high as 10.0, but it's going to be in that general vicinity. Now, glutamic acid, on the other hand, is going to be 9.47. Okay, so those are both basic groups. Chances are, at a physiological pH of 7.4, those 2 groups are going to be completely protonated. Now, if we move over to the C termini, so the carboxylic acid on the right-hand side of my 2 molecules, those 2 groups, well, they have acidic pKa's. So aspartic acid is going to have a pKa of 1.99 on its carboxylic acid, on its C termini, whereas glutamic acid is going to have a pKa of 2.10. Now, if I move over to, so those 2 are pretty comparable to one another. If I move over to my R group, well, my R group is going to, for aspartic acid, have a pKa of 3.90, whereas glutamic acid is going to have a pKa of 4.07. Okay, so the way that I've drawn this is I've drawn these 2 molecules when they are completely protonated. So the pH is less than all of the pKa's. So when my pH is lower than my pKa, then you can conclude the group will be protonated. Now, if you look at these groups, one thing that's important to think about is this is where they've maxed out. You can't add any more protons to these groups. So if you look at the N-termini of aspartic acid or glutamic acid, it's NH3+. You're never going to see NH4++ because that nitrogen can't take on that fifth bond. So if you look at that carboxylic acid, you're never going to have a positive charge there. The only thing that that carboxylic acid is going to do for any one of these groups is, well, it can lose the proton and become negatively charged. Now, in the event that you see something like where I'm just drawing this star right here, what does that tell you? Well, this group is deprotonated, indicating that there's a negative charge there. But also that indicates that the pH of the solution that this molecule is currently residing in, the pH is greater than the pKa. Okay, now, if you have any questions about that, please reach out to me on my Facebook page, facebook.com/chemventure, and we can set up a time for a tutoring session. And I hope this was helpful, so have a good one.